In chapter 5, we shall solve Abel integral equations. This chapter is divided into two modules, module 1 and module 2. In module 1, we shall solve Abel integral equation by a very simple method based on elementary integration. Now we consider simplest form of Abel integral equation, which is given by equation 5.1. Here the unknown function is phi t and the kernel of the integral equation is given by x minus t to the power minus half. The range of integration is from 0 to x. This Abel integral equation has been derived in chapter 1, module 2, and it comes from historic Abel problem. The upper range of integration is variable. So, this integral equation is often referred to as Volterra integral equation of first kind. Now we shall solve this simplest form of Abel integral equation by using a method based on elementary integration. We multiply equation 5.1 by the function y minus x to the power minus half and integrate with respect to x between 0 to y to obtain integral 0 to y fx divided by y minus x to the power half dx, that is equal to integral 0 to y integral 0 to x phi t dt divided by root over x minus t root over y minus x dx. Now, this double integral can be further simplified. First of all, we interchange the order of integration. This interchange of order of integration has been explained in chapter 1, module 2, and we use this standard method to interchange the order of integration, where the t integral now becomes the outer integral and the x integral now becomes the inner integral. Range of t integral is from 0 to y and the range of x integral is from t to y. Now, the inner integral can be further simplified. If we substitute x equal to y sin square theta plus t cos square theta, we find that this inner integral becomes equal to pi. Very simple integration is involved. Now we substitute the value of inner integral as pi in equation 5.2 to obtain integral 0 to y fx divided by root over y minus x dx equal to pi into integral 0 to y phi t dt. The unknown function occurs in the right hand side under the sign of integration, which is from 0 to y. So, we differentiate both sides with respect to y to obtain the solution of Abel's integral equation 5.1 as phi y equal to 1 by pi d dy integral 0 to y fx divided by root over y minus x dx as given in equation 5.3. Now, equation 5.3, here phi y is the solution of Abel integral equation 5.1, where the upper range of integration is variable. If the lower range of integration is variable and upper range is a constant, then the integral equation is given by equation 5.4. Here the range of integration is from x to b, and of course fb equal to 0, and the kernel is root over t minus x to the power half. This is another form of Abel integral equation. The solution of this Abel integral equation can be obtained in a similar manner, and we can note that the equation 5.4 can be put in the form given by equation 5.1 by changing the order of integration from b to x with a minus sign. So, the solution of this integral equation is given by 5.5, and the difference with the solution of first type integral equation, that is equation 5.3, that there is a minus sign before in equation 5.5. Next, we generalize this Abel integral equation slightly by considering the equation given by 5.6. Here, the kernel of the integral equation is x minus t to the power alpha, which is in the denominator of the right hand side of equation 5.6, and this alpha lies in the interval 0 to 1. Here of course f0 is equal to 0. We shall now solve this generalized form of Abel integral equation by the method based on elementary integration. For this, we multiply both sides of this equation, that is equation 5.6, by the function y minus x to the power alpha minus 1 and integrate with respect to x from 0 to y. We obtain integral 0 to y fx divided by y minus x to the power 1 minus alpha dx equal to a long expression on the right hand side which involves double integration. The inner integral is with respect to t, which ranges from 0 to x, and the outer integral ranges from 0 to y and is with respect to x. We now interchange the order of integration in a standard manner described before to obtain an expression where the t integral is the outside integral which ranges from 0 to y, and the inner integral is the x integral which ranges from t to y. This inner integral can be further simplified. If we substitute x equal to y sin square theta plus t cos square theta, then the value of this integral comes in terms of beta function, that is beta 1 minus alpha alpha. Now, beta function can again be written in terms of gamma function, which is given by gamma alpha into gamma 1 minus alpha divided by gamma 1. Now, gamma 1, we know that it is equal to 1. Also, we know from the theory of gamma function that gamma alpha into gamma 1 minus alpha can be written as pi by sin pi alpha. So, we see that the inner integral, that is the x integral, simplifies to pi by sin pi alpha. And if we substitute this value of inner integral, then we obtain integral 0 to y fx divided by y minus x to the power 1 minus alpha dx. This is equal to pi by sin pi alpha integral 0 to y phi t dt. So, here we see that the unknown function comes under the sign of integration, where the range of integration varies from 0 to y. So, to obtain phi t, we differentiate both sides of this expression with respect to y, and we get the solution of slightly generalized Abel integral equation as phi y equal to sin pi alpha by pi d dy integral of 0 to y fx divided by y minus x to the power 1 minus alpha dx as given in 5.7. So, this is the solution of the Abel's integral equation, where the upper range of integration is variable. Next, we consider this general Abel integral equation where the lower range of integration is variable. That is, integral from x to p phi t minus x to the power alpha dt equal to fx. Here also fb equal to 0 and alpha lies between 0 and 1. The solution of this integral equation can be obtained in a similar manner, and we obtain the solution phi y equal to minus of sin pi alpha by pi d dy integral y to b fx divided by y minus x to the power 1 minus alpha dx, as given in equation 5.8. Next, we find Abel integral equation's solution, and we consider most general type of Abel integral equation given by equation 5.9. Here the range of integration is from a to x, that is, the upper limit of integration is variable and the kernel is given by 1 by hx minus ht whole to the power alpha. Here also f a equal to 0 and alpha lies in the interval 0 to 1, and hx is a function which is strictly monotonically increasing and differentiable in the closed interval ab. Also, h dash x is not equal to 0 in the closed interval ab. The solution of this most general form of Abel integral equation is given by equation 5.10. Here on the right hand side, the t integral is from a to x and the integrand has got h dash t, which we have assumed not equal to 0 in the interval a to b. Next, we consider another type of Abel integral equation where the lower limit of integration is variable and the kernel is the function 1 by ht minus hx whole to the power alpha. Here also we assume that ht is monotonically increasing and h dash t is not equal to 0 and ht is differentiable in the closed interval ab. Its solution can be obtained similarly by phi x equal to minus of sin pi alpha by pi ddx of the integral x to b f t h dash t divided by ht minus hx to the power 1 minus alpha dt. X lies in the interval a to b. Thus, we have used a method based on very elementary integration to solve Abel integral equations. Now, we shall use this method to solve two problems. Now, in example 1, we will solve the Abel integral equation given by equation 5.13. Here, the forcing function is pi into x plus 1 and the kernel of the integral equation is 1 by root over x minus t. We multiply this equation on its both sides by the function y minus x to the power minus half and integrate with respect to x from 0 to y to obtain an expression pi into integral 0 to y x plus 1 divided by root over y minus x dx equal to an expression which consists of double integral. As before, we interchange the order of integration to obtain the expression given by pi into 4/3 y to the power 3 by 2 plus 2 root y equal to the expression given on the right hand side. As before, the inner integral, that is the x integral, can be simplified by substituting x equal to y sin square theta plus t cos square theta to get pi, and so we can write integral 0 to y phi t dt equal to 4/3 y to the power 3 by 2 plus 2 into y to the power half, which on differentiation gives phi as given in equation 5.14. So, this is the solution of the Abel integral equation by the method we have illustrated so far based on elementary integration. In example 2, we solve the Abel integral equation where the kernel is 1 by root over x square minus t square as given in equation 5.15. Here we substitute x square equal to u, t square equal to v to obtain the integral equation as given in 5.17. Here phi 1 is related to phi and f1 is related to f through the relation given by 5.18. Now 5.17 is the integral equation which is in very standard form. We can solve this integral equation by the elementary integration as shown before to obtain the solution given by phi 1 equal to 1 by pi ddv of integral 0 to v f1 u root over v minus u du. So, we get back to the original function phi y through the relations 5.16 and 5.18 to obtain the solution of Abel integral equation 5.15 as given in equation 5.19. We have used a very simple method based on elementary integration to solve Abel integral equation, and we have used this method to solve simplest form of Abel integral equation where the kernel is of the form 1 by root over x minus t. Also, we have generalized this Abel integral equation by taking the kernel as 1 by x minus t to the power alpha, where alpha lies in the interval 0 to 1, and finally the most general form of Abel's integral equation, whose kernel is given by 1 by hx minus ht to the power alpha, where hx is a monotonically increasing function which is differentiable and h dash t is not equal to 0. So, this method is very simple method to solve this Abel integral equation.